And welcome to Unit 2, Lesson 2, where we're going to discuss arithmetic sequences and partial sums. You need to be able to recognize, communicate, and use arithmetic sequences to model real-life problems. So consider the following sequence. We have -4, then 2, 8, 14, 20, and 26. By the end of the lesson, you would be able to write a formula to define the nth term. If you notice, we keep adding 6 to each term. The consecutive terms have a common difference. In other words, these look like numbers that would be generated by a linear function. These are called arithmetic sequences. A sequence of numbers whose consecutive terms have a common difference is called an arithmetic sequence. A sequence is arithmetic if the differences between the consecutive terms are the same. So if we have a sub 1, a sub 2, a sub 3, a sub 4, all the way to a sub n, so the first term, the second term, the third term, the fourth term, all the way up to the nth term, that is considered arithmetic if there is a number d such that when you take the difference, if I take a2 minus a1, and a3 minus a2, and a4 minus a3, you get a common difference of the arithmetic sequence. So let's determine whether or not the following is arithmetic, and if it is, find the common difference. So if we look at A, if I take 9 minus 4, it equals 5. If I take 14 minus 9, that also equals 5. If I take 19 minus 14, that equals 5. When I take 24 minus 19, it yields 5. So in each one of these cases, when I took a term minus its previous term, per the definition, I got a common difference of 5. So this is an arithmetic sequence because the common difference, or the variable d, is 5. Now let's look at example B. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. If I simplify those, I get 1, 4, 9, 16, and 25. If I take 4 minus 1, it equals 3. However, if I take 9 minus 4, that equals 5. Already you can tell I don't have a common difference. I'll keep going. 16 minus 9 equals 7. And 25 minus 16 equals 9. This would not be an arithmetic sequence because the differences between the terms is not common. On this example, we're going to find the first 5 terms of the sequence, and we're going to assume n begins with 1. What is our common difference? Well, when I want to find the first term, I take the number 1 and I substitute it in for n. So I get 1 plus 1 minus 1, which is 0, times 4, which yields 1 plus 0, which is 1. So the first term of the sequence is 1. To find the second term of the sequence, I substitute in 2 for n. So a sub 2 equals 1 plus 2 minus 1, which is 1 times 4. So 1 plus 4 yields 5. For the third term of this sequence, I input 3. So 1 plus 3 minus 1, which yields 2, times 4 gives me 8. 1 plus 8 yields 9. For the fourth term of the sequence, I input 4 in for n. So 1 plus 4 minus 1, which is 3, times 4 gives me 12. 1 plus 12 is 13. For the fifth term, I input 5 for n. So 1 plus 5 minus 1 times 4. So that's 4 times 4, which yields 16. 1 plus 16 equals 17. You might have been able to just look at the first few terms to generate the rest of them based on the common difference. When I go from 1 to 5 to 9 to 13 to 17, that was a difference of 4 each time, so my common difference is 4. The nth term of an arithmetic sequence has the form a sub n equals dn plus c. So you can think of that as a kind of mx plus b in linear form. However, instead of it being the slope, d is considered the common difference, and c, which you would have known as maybe as the y-intercept. So c is equal to a sub 1 minus d. So to translate, you're counting by D's. You're counting by that common difference. And you begin by shifting C units from D. So for example, if I have 2, 6, 10, 14, and 18, it's a common difference of adding 4. And if I take that C equals a sub 1, which is 2, minus my common difference of 4, that yields -2, or otherwise known as my y-intercept. So the formula that describes 2, 6, 10, 14, and 18 is 4n minus 2, where 4, or the D, represents my common difference, and -2 represents the distance between the consecutive terms of the sequence, where C equals A1 minus D. So let's look at the sequence 6, 11, 16, and 21 and come up for a rule for how to find nth terms of this arithmetic sequence. Well, if I'm using the formula similar to mx plus b, but now that we are in sequences, we use a sub n equals dn plus c, I have to find d and c. D is our common difference. So if I take 11 and I subtract 6, it yields 5. If I take 16 minus 11, it also yields 5. If I take 21 minus 16, it yields 5. So my common difference in this case, in this pattern, is 5. So far I have a sub n equals 5n plus c. But now I have to find c. Well, I know that c is equal to a sub 1, which is my first term, subtract my common difference. So my first term is 6, my common difference is 5, and when I subtract them it yields 1. So let's put this all together. When I put this all together, I'm going to use the formula a sub n equals dn plus c. I know that my common difference is 5 and my c is 1, and that's my final answer. How can I check it? Well, let's recall the pattern. Okay, the pattern was 6, 11, 16, and 21. If I use my formula to check, when I want to find a sub 1, and I plug 1 back into the formula that I have derived, 5 times 1 is 5 plus 1 is 6, and that does yield the first term of the sequence. If I look at a sub 2, 5 times 2 plus 1 equals 11, and that is the second term of my sequence. If I look at a sub 3, 5 times 3 is 15 plus 1 is 16, which yields the third term. And finally, a sub 4 equals 5 times 4, which is 20, plus 1 is 21. So my rule of a sub n equals 5n plus 1 does work for the entire sequence. On example 2, we're going to find a formula for the nth term of an arithmetic sequence. So again, we have to find that formula. So I have to find d and c. Well, they gave me d. There's not a whole lot of work here. So if I use the formula a sub n equals dn plus c, I automatically know 4 is d because they gave it to me. What I have to do is find c. So if I know that c is equal to a sub 1 minus d, my first term that was given in the problem was 15. My common difference is 4. 15 subtract 4 gives me 11. So when we put this all together, again, using my formula a sub n equals dn plus c, then my d is 4, my c is 11, and you can check this. If I want to find the first term using that formula, I substitute in 1 for n. 4 times 1 is 4, plus 11 is 15, and it yields the first term of this sequence. Now I want you to notice example B. We really aren't doing anything different. We're still dealing with the formula a sub n equals dn plus c, but I gave you information a different way. I gave you a sequence of numbers. So in order to find d and find that common difference, I think a lot of you intuitively understand what's going on, but by definition of an arithmetic sequence, if I take 5 minus 10, I'm getting -5. If I'm taking 0 minus 5, I'm getting -5. If I'm taking -5 minus 0, that is yielding -5. If I'm taking -10 minus a -5, that is also yielding -5. So my common difference in this sequence by taking a2 minus a1, a3 minus a2, a4 minus a3, and so on, is a difference of -5. Well, what is C? I still go back. C is equal to the first term of the sequence, subtracting off the common difference. So the first term is 10. I'm going to subtract off the common difference of -5. So my C is 15. So how can I put this all together? If I use my a sub n equals dn plus c, and I substitute in -5 for my d and 15 for my c, I now have my formula a sub n equals -5n plus 15. Again, this is not a necessary part of the problem, but you can easily check your answer by seeing if your final answer matches up with the sequence that was given. So if I want to find the first term of this sequence, -5 times 1 is -5 plus 15, which equals 10, which indeed is the first term of the sequence. When I input 2, -5 times 2 is -10, plus 15 is 5, which is the second term of my sequence. When I input 3, -5 times 3 is -15, plus 15 gives me 0, which is the third term of the sequence. Okay, when I input 4, I should yield -5, which I do. -5 times 4 is -20 plus 15. When I input 5 and I get -5 times 5 plus 15, that does equal -10, which is the fifth term of my sequence. For this example, we're going to write the first 5 terms of the arithmetic sequence and verify with the table feature on your graphing calculator. So on here, how are the two terms related? This is what is kind of different about this problem. Instead of giving you the first term and the common difference, I'm giving you the fourth term and the 10th term. So how are these two terms related? Well, think of it this way. If I gave you the fourth term and the 10th term, then they're 6 terms apart. So if I wanted to find the 10th term and started with the fourth term, I would have to add 6 differences. So I would take a to the fourth, which is 16, and I would have to add the common difference 6 times in order to get to 46. Well, let's do a little algebra. I can do some substitution. I know that a sub 10 is 46 and a sub 4 is 16. Then if I solve for d by subtracting 16 from both sides and then dividing by 6, I come up with the common difference is 5. So now that I know the common difference is 5, if I went ahead in the sequence, and I know that the question asks for the first 5 terms, but just to kind of fill in the blanks for you, 16 plus 5 gives me 21, so that would be the 5th term of this sequence. Add 5 to that, and I would get 26. So that would be my 6th term. Then if I add 5 to that, I get 31. So 31 is my 7th term. In order to get the next term, I would add 5, which would be 36. And you can see kind of the pattern of what's going on. The next number would have a 1 in the ones place, so it's going to be 41. If I go backwards, then I would have to subtract the common difference. So 16 minus 5 is 11. So the common difference here is 11. I'm sorry, the common difference is 5, so the third term is 11. If I take 11 minus 5, I get 6. So the second term of the sequence is 6. And the first term would be 6 minus 5, which is 1. And so I now know the first 5 terms of the arithmetic sequence. 1, 6, 11, 16, and 21. Now, if we want to verify this on our graphing calculator, we're going to have to be able to come up with an equation formula for this. So if I have a common difference of 5, C is going to equal my first term, which is 1, subtract my common difference of 5, so that yields -4. So when I go and type this into my graphing calculator, I want to make sure I pull up a graphs page. I need to set the graph entry edit to sequence. And my common difference of this problem was 5. So I have 5n. And then my C value was -4. And then if I hit Control T, I get a table of values. And notice how I get 1, 1. My first term is 1, my second term is 6, my third term is 11, my fourth term is 16, and my fifth term is 21, which does match what the first 5 terms were of my sequence. Now we're going to switch gears to recursion. And remember from our last unit that recursion requires a couple of terms already in the sequence to determine the next term in the sequence. So if you know the nth term of an arithmetic sequence and you know the common difference of the sequence, you can find the n plus 1th term using the recursion formula a sub n plus 1 equals a sub n plus d. Why does this work? Well, from our last example, didn't we have the first 5 terms as 1, 6, 11, 16, and 21? So your first term is 1, your second term is 6, your third term is 11, your 16 is your fourth term, and 21 is your fifth term. So putting this all together, I can think of 6, which is the second term, as the first term plus 5. I can think of 11, which is the third term, as the second term plus 5. I can think of 16, which is the fourth term, as the third term of 11 plus 5. I can think of the fifth term, which is 21, as the fourth term of 16 plus 5. So those are the specific examples. Then we can use the general, is if you take a n sub 1, so if you take the term 1 more than n, you take n plus the common difference to get that value. Now, if you substitute a sub 1 minus d for c in the formula, okay, so here is our a sub n equals d sub n plus c, our y equals mx plus b, so to speak, for these arithmetic sequences. Okay, you yield what's considered an alternative recursive formula. So if I put in a sub 1 minus d in for c, I can use the commutative property for addition, and I can switch the order in which I'm adding d sub n and a sub 1 to rewrite it as a sub 1 plus d sub, or dn minus d. Next, I can factor out a d, and this is my alternative recursive formula. Why is this powerful? It is recursive, that's where it stems from, but it's not that recursive at all. If you know the first term and the common difference, you can yield any term a sub n in the sequence. So for example 4, let's write the first 5 terms of the arithmetic sequence. We're going to find the common difference and then write the nth term of the sequence as a function of n. So notice how they gave me that the first term was 200. So that's a no-brainer. The first term is 200. Then they gave me the recursive formula a sub k plus 1 equals a sub k minus 10. So if I want to find a sub 2, that means I have to take a sub 1 minus 10, which is 200 minus 10, which yields 190. When I want to take a sub 3, using the formula a sub k plus 1 equals a sub k minus 10, I have to take a sub 2 minus 10. From the previous step, a sub 2 is 190, and when I subtract 10, I get 180. Following that same pattern, and a lot of you might not need all of the work, hopefully you get it that you keep subtracting by 10, but notation is important. So when I have a sub 4, that is equal to the recursive pattern a sub 3 minus 10, or the previous term, subtract 10, and 180 minus 10 is 170. A sub 5 is equal to the fourth term minus 10. The fourth term is 170 minus 10, which yields 160. So my common difference in this case is negative 10. So how do I write a general formula? Well, I'm going to use the alternate form of the recursive formula. A sub n equals the first term plus n minus 1d. Well, my first term is 200, and my common difference is 10. Next, I distribute the negative 10 to get 200 minus 10n plus 10. And when I combine like terms, my recursive formula is negative 10n plus 210, writing the nth term as a sequence as a function of n instead of the recursive formula that was given, a sub k plus 1 equals a sub k minus 10. On example 5, you're given the first 2 terms of the arithmetic sequence, and you have to find the missing term. We'll check our answers using the table feature on your calculator. So I was given that a sub 1 equals 3, and a sub 2, or the second term, is 13. So I can deduce if I take 13 minus 3, I yield 10. So that means that my common difference is 10. Now, you could do this quote-unquote the long way. I could simply, knowing that my common difference is 10, I could say a sub 1 is 3, a sub 2 is 13, and I could keep adding 10. So a sub 3 is going to be 23. A sub 4 is going to be 33. A sub 5 is going to be 43. A sub 6 is going to be 53. Again, I'm just adding 10 to each term, to the previous term. The 7th term is going to be 63, the 8th term is going to be 73, and the 9th term is going to be 83. So that is one way that you could have gone about this problem. But 9 wasn't too bad of a number. What if we wanted you to find a sub 100? In my opinion, this would not be an efficient way to figure that out. So we need another way. Well, I can try to write a formula in terms of n, a function where I put in the 9th term, the 50th term, the 100th term, and then I can output that number in the sequence. So if we use our alternative recursive formula, where all I need to know is the first term and the common difference, I can input 3, which is my first term, 10, which is my common difference. I can distribute the 10 to get 10n minus 10. I can combine like terms to get 10n minus 7. And then now I could use that formula to input 9. So when I take 10 times 9, which is 90, minus 7, it yields 83, which is the same answer I got using the quote-unquote long way to figure that out. Now we can check our work on a graphing calculator. So it's really up to you how you want to do it. You could use it by using the table feature or the graph. So I can press menu, add graphs. I can change this to sequence mode. We found that our formula was 10n minus 7. So I'm going to type in 10n minus 7. Then if I hit Control T to get a table, we can see all of my answers. There's a sub 1 is 3, or all my different terms. A sub 2 is 13, a sub 3 is 23, 33, 43, and come on. And there we go that the 9th term is 83 to verify my results. For our last example, we're going to use a graphing calculator to graph the first 10 terms of the sequence, assuming n is 1. So we have a sub n is equal to negative 5 plus 2n. So if I go to my calculator, press menu, we want to go to a graphs page. We want to switch the graph entry or edit to sequence. And we're going to type in our function negative 5 plus 2n. So negative 5 plus 2n. We're going to keep the initial terms blank, and we want each step to be 1. So when I hit enter, notice how you can see the first 1, 2, 3, 4, 5, and the remainder are going to go up. So what you can do is on the axis, you can pull it down until you get, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and we just have slightly right there. We can get a good picture of the first 10 terms of the sequence. So our learning opportunity is page 573, and you can start working on 1 to 51 odd. Good luck. Congratulations.